Good morning, everyone. Thank you very much for joining this morning session. In the next 20 minutes or so, I would like to talk to you about one of the most fascinating yet challenging problems that I had to tackle in my short but quite intense career. My name is Simon. I am a senior applied scientist at Gauss Lab for the machine learning and data science team. In this team, I implement, design, and deploy machine learning systems that are running in semiconductor fabs. Today's presentation will be about AI-powered metrology for high-volume manufacturing. Now, if you're not from SK Hynix or if you're not a data scientist, this title will probably seem very complicated and have very little meaning. So my promise to you is by the end of this presentation, you will have a clear idea of what this means, and you will probably have learned a couple of things that you can take to your own fields. Let's start by acknowledging some very simple facts. Chip making is an incredibly complicated manufacturing process. It is probably more complicated than making cars, aircraft, perhaps even rockets. And the reason for that is that building a single memory chip, which is the kind of chip that SK Hynix focus on, takes enormous amounts of steps. There are thousands of steps, each of which is specific, complicated, requires advanced physics, and is done at a very, very small scale. Because it's so complicated, the engineers actually have to measure things all the time. So there are, perhaps tens of thousands of measurements devised throughout the fab to make sure that the processes are going correctly. And then finally, as you can probably all imagine, a fab contains lots of machines. Of those machines produce data. All those sensors produce data. So this is the first piece of the puzzle. This is the high volume manufacturing environment. We're building chips at a very large scales with many machines and many chips. So this is a complicated problem. But let's look more precisely at what it looks like to get a precise idea. This is what a step looks like inside of a fab. You have those gray disks, which are called wafer, sometimes also called substrates. This is where the chips are going to be built. Usually what happens is that they go in sequence into what's called a processing equipment, which will do some operation on that substrate. So for instance, it's going to deposit some material, it's going to remove some material, it's going to create some patterns that the chips needs to have engraved upon. Afterwards, it goes on to the next step. And this goes on like this 1,000 times. But each step is very different. The operation is going to be different in this processing equipment, which makes it very complicated. So to make it controllable, the engineers have what we call metrology equipment. So metrology simply means measurement. So they're going to take one of the process substrates, and they're going to look at the properties of that substrate and decide whether the process is going on well or not. Now, if you're a data scientist and you're curious about data generation process, you can imagine that you get tons of data because the processing equipment is going to generate sensor data, we're going to have measurement data, and we need to make sense of all of this. This is a huge scale. There is a huge diversity of processing equipment and of metrology equipment. And so this is beyond the comprehension of any single individual. For each of those steps, you have, field engineer specialists that are responsible for understanding, calibrating, operating those machines. So a single human cannot have a full picture of the fab. And this is a problem because engineers have essentially only limited visibility. If you go back to the picture before, you can notice that after each processing step, we are not going to measure everything. Because measuring things inside of a fab is complicated. It takes time, it takes place, it takes money, it takes effort. So engineers only measure the strictly required minimum to get the fab running. So they only have limited visibility, and as a result, they cannot manage yield, process equipment as efficiently as they should. So to take a simple comparison, you could imagine a captain flying an aircraft that has access to altitude and speed, maybe only 5 or 10% of the time. You probably would not want to get on that aircraft. It's sort of like the same thing. for chip manufacturing. More fundamentally, if we look at this lengthy quote from the physicist Lord Kelvin, you can realize that not being able to measure things is actually a fundamental problem. It's a fundamental problem because if you cannot express something in numbers, you only have a very partial understanding of that phenomena. If we put it in shorter form, we can say that if you cannot measure it, you cannot improve it. So now we're starting to get a better picture. We have the fab, the high-volume manufacturing fab that generates this immensely complicated data. We have the engineers that want to have more visibility into the process, but they cannot do so because they cannot measure everything all the time. And so this is where AI comes in. If we've learned something for the past decade or so, is that AI systems, machine learning systems, are very good at finding patterns in complex data where human cannot. So we have a need, a problem, and a solution. The need is that engineers need this full visibility. The problem is that we cannot measure everything. So a potential solution is, why not let's try to use AI to predict what is not measured. And this is the problem that Gauss Labs solves. This is essentially an AI task, a machine learning task, and this is what AI-based metrology is about. This is what virtual metrology is about, and this is the main solution that we develop at Gauss Labs. Now, if you're a seasoned data scientist or machine learning engineer, you may think that it's just like any other machine learning task. But if you're also an experienced scientist, data scientist, you will know that, as we've seen earlier, a lot of AI models, a lot of machine learning solutions fail to deliver value. And each problem has their own challenges. So let's go over the one of virtual metrology. What makes operating machine learning models inside of a semiconductor chip factory more complicated or complicated compared to other machine learning challenges? First of all, as you probably understand by now, the complexity is enormous. We have all those steps, we have all those equipments, we have all those physical processes happening at a very tiny scale. We cannot have one big model to rule them all. We cannot just do the same thing that works very well for LLM, for instance, where you just essentially dump enormous amounts of text into a model and let it learn from it. Here you need to actually think a little bit about how you're going to organize and aggregate your models. The second problem is that paradoxically, there is a scarcity of data. We have enormous amounts of sensor data, but the really interesting data about the object that's being manufactured is very scarce. As I said earlier, we don't have full visibility. This is the problem that we're trying to solve. So of course, we only have very few measurements to use to train our models. The third challenge is changes. In a fab, which is an extremely complicated environment, things change all the time, basically on a weekly, even on a daily basis. On one week, a certain team is going to operate an equipment. The next week, another team is going to operate that equipment. Perhaps a machine will break down. Perhaps a machine will be recalibrated. And you can imagine, in terms of data generation process, that each of those operation, each of those action will completely change the distribution of the underlying data. So you need to have adaptive model. Because if you naively fit your XGBoost model or the latest neural network that you've implemented, it will work for a week, and then in 2 weeks, the prediction will be completely off. So that's an enormous, perhaps the most complicated challenge. And then finally, a challenge which is common in many machine learning problems is the scale. We have the thousands of steps. Each step creates time series data, actually time series of time series data with various sampling rates and sampling frequencies. And so you get data that you cannot just open in your, let's say, Jupyter notebook and try to do some analysis with. You need to have some sort of scalable computing. So this is why Gauss Labs actually built Panoptes VM, so Panoptes virtual metrology, to solve this problem. So here is a very, very simple diagram to recap and make sure everybody's following. We have the sensor data and the past measurements. That's essentially all the data that's generated by the fab. We have our predictive model. and we output some virtual measurement, right? The thing that the engineers are interested about. For instance, if you're a process engineer, you may be familiar with thickness, refractive index, critical dimension, tilt, warpage, etc., etc. And the purpose, the raison d'être of Panoptes VM is that it solves the complexity, the scarcity, the changes at scale. So it's not just like any, we could make a comparison with other AutoML solution. It's more of a purpose-specific machine learning solution. We can start by looking at the complexity and the scarcity. Remember, we have this fab with many different kind of equipments, very different kind of data sets, all of which are slightly different, and a single model cannot tackle them all. But of course, it would be also another problem to try to fit a separate model on each of the equipment and each of the steps within the fab. So we developed what's called aggregate modeling, where you can take some steps, some equipment, and aggregate them in we could say smart ways or non-obvious way to create a larger data set. So perhaps you will have 10 data sets with 100 points, and you can aggregate them to get maybe 1,000 points, for instance. And then you can fit your model, and your model will perform much, much better. And you can do that at various scales. So you can end up with very, very large data sets, which will perform much better than if you have taken, for instance, the naive approach. The other benefit of this approach, as you can guess, we said that there is a scarcity problem. If you can aggregate things, you get better and bigger data sets. And so this aggregate model also solve this issue. Now, if you're interested about the technical detail, this could be the topic of a full session on its own, so you can check the reference provided. As I said earlier, one of the problems is the rate at which changes occur inside of the fab. How we solve this, again, is we developed our own method called we implemented our method, adaptive online learning. And the whole purpose of this method is to automatically and sort of like by algorithmic design handle the changes inside of the fab. The typical solution is going to be to regularly retrain your model with some heuristics. Here, the adaptivity is actually built in within the model. And so the way you can see it is you have your input data, which is going to be, remember, the sensor data, maybe past measurements. You have your target, which is the measurement. And you're going to do some time-dependent normalization to bring all the data into some stable distributions. So you can think of it as removing seasonality, for instance, in time series. It's not exactly the same, but it's essentially the same idea. Once we have data that is more stable, we can then feed it into what's called an adaptive online regressor. And this regressor is going to adapt to sudden change in the data. So as I said earlier, sometimes the machine is going to be calibrated differently. And this is going to completely change the relationship between the input and the output. And this class of algorithm can actually capture those changes very effectively. Now you can very briefly look at the diagram below. Essentially, the idea is that the green curve is what we're trying to predict, and the red curve is our solution. Of course, this is synthetic data, but it gives you the idea. You can see before the big shift around 200 timestamp, you can see all the models are performing well. So that's what you would do as a data scientist, training an offline model. But then suddenly, once the jump happens, you can see that the gray curve and the purple curve simply are not following up with the new trend. So Panoptes solve this problem through adaptive online learning. Finally, how does Panoptes handle scale? Because up until now, what we've talked about is mostly, we could say, theoretical or conceptual. But as you know, if you have been working on any ML project, you will realize that one of the challenges is to scale the solution, to deploy it, to make it reliable. It's one thing to code something up, an analysis in a notebook or on a script, and have some model that performs well on a specific data set. But it's a completely different thing to have a full-on system that is going to work reliably all the time. The typical setup for a data science or machine learning project is that you will have one problem, you will have one or a few models, a data set, and a data scientist. And there will be some iteration, right? The data scientist is going to collect the data, train the model, look at the results, maybe deploy it, get some feedback, do some, again, manual operation to maybe cleanse the data, maybe create some new features, etc., and so on, until the customer or the end user is happy with the results. Now, if you remember from the beginning, we are in a high-volume manufacturing environment. There are thousands of steps. So if you were to take this route, you would need basically at least 1,000 data scientists, which of course is not scalable, is extremely expensive, and essentially defeats the purpose of using AI to automate things, right? The way Panoptes work is that we automate things as much as possible, so that a single data scientist or a field engineer, actually doesn't have to be a data scientist, it can be somebody that doesn't understand much about the underlying model or any topics of data science, is going to be able to train and operate many models at the whole fab level. So a single field engineer, maybe which is responsible for a very specific area of the manufacturing process, is going to be able to set up 10, 20, 50 models to actually understand what is going on in his specific field. And he's not going to have to worry about hyperparameter optimization. He's not going to have to worry about data collection. He's not going to have to worry about any of those things. So in a sense, it's quite close to some automated machine learning solution, but again, it's purpose specific, and it really takes into account the specificity of this very complex and again very specific environment. Now, of course, it's a lot of talk to understand the concepts, but what is the actual outcome of all this? Does this actually work? Does this actually bring any values to the engineers? And we have some evidence of this. So here, for instance, we have a testimony from a thin film process engineer at SK Hynix, which tells us that when Panoptes VM is connected to a process control such as APC, process variability decreases and yield increases. So if you remember the problem statement that we had earlier, where we have limited visibility, so engineers cannot control the process so let's try to predict with some AI. You can see the problem is essentially solved, right? We stated a problem and we delivered on the solution. Again, you can check out some details. There are some actually accurate numbers here. I didn't want to bury you under some very specific numbers, so you can look into the detail for that. What's very interesting with Panoptes VM is that you can imagine that when you're able to go from a state where you have very limited visibility to a state where you have full visibility on what's going on, you have lots and lots of possibilities, right? And just like, again, if we take the comparison from before with the pilot flying his airplane, he cannot fly the same way if he doesn't have very precise instruments and if he's just flying at sight. Here is exactly the same thing. So because we are able to produce scalable, accurate, and also usable by engineers systems, engineers can do a lot of various things with those virtual measurements, such as as we said earlier, reducing the process variability, excursion detection, which means essentially finding problem before they happen, tool monitoring, again, which is checking the status of the various tool, yield analysis, making sure that they're using the resources as best as possible, sampling rate optimization, meaning that they can actually optimize how they measure things inside of the fab, and finally dynamic sampling. What is the bottom line of all this? Is this a problem worth solving? As we seen earlier, there is very few AI project that actually delivers value, and sometimes it's because the benefits are misestimated from the get-go. Not everything can be solved through AI, and not everything solvable through AI is actually worthwhile. But here, from the beginning, we have strong evidence that this is the case. If you compare, for instance, our solution with an average metrology cost equipment, it's around 2 million. there are hundreds and dozens and hundreds of metrology equipment within a fab. So that represents enormous amount of money, and the metrology market again is very large. And if with AI you can make a very small change, because the scale of chip manufacturing is so large, you can very easily get a lot of financial benefits from it. Thank you very much for listening. I hope you enjoyed this presentation. Before I let you ask some questions, I would like to remind you that we have a booth downstairs, and if you have more questions on Gauss Labs to me or what we do, I will be gladly answering them, or my colleagues.